Chapter 14, Correlation and Regression. I'll walk you through these PowerPoint slides so we can focus on the learning objectives. There is some material that has been omitted, so this will help you focus on the necessary material to complete the homework assignments. Our learning objectives. Number one, we'll understand the Pearson R as a measure of variables relationships. So our focus is on how are variables moving together. Correlation is defined as the relationship between variables whereby a change in one variable results in a concurrent change in the related variable. Again, concurrent meaning at the same time. So if we see one variable increase or decrease, what does that mean for the related variable? That is, if they are related at all. Number two, compute Pearson R using the definitional or computational formula. So we're going to review both processes that we learned in Chapter 4. We've been accustomed to using the computational formula throughout the semester. So we're going to refresh our memory of the definitional process and see it in terms of how it could be utilized for our regression equation calculations. Number three, use and interpret Pearson R, understand assumptions and limitations. Again, we'll understand the range in which our correlation coefficient can reside, and then the limitations of interpreting that particular statistic. Number four, test hypothesis about population correlation. This Greek letter is referred to as rho. And we'll test rho to determine if we see a relationship between variables in a population using sample statistics. And going on to our next, then we'll get to our regression components of this chapter. So number 6 says, explain, compute linear regression equation to predict y values, and 7, evaluate significance of regression equation. So we're going to conduct an F ratio test to determine if the correlation coefficient is significant, as well as if the linear regression we've calculated is significant. Okay, so the tools you will need: sum of squares using computational and definitional formula. So back from Chapter 4, we learned that SS, using the definitional formula, was equal to, just as it states, sum of square deviations. It's the sum of x minus the mean of x squared. Again, by definition, we compute the deviation in the parentheses, and then we square those deviations, and then we take the summation, and that leaves with the sum of squared deviations. That's the definitional process. So this relates to the definitional. The computational formula, as we've become quite accustomed to using, is the sum of x squared minus the sum of x squared over n. And again, we refer to this computational because we don't see the calculation of mean deviation as we do here in the parentheses. It saves us time. It's pretty effective in minimizing the steps necessary to calculate SS, but we'll see that using the definitional formula is a little easier and more efficient when we're calculating our regression equation. Hypothesis testing from Chapter 8, again, determining the significance of the relationship, will be put to a test using either a t-test or an F ratio test. So understanding analysis of variance. So Chapter 12, we learned about the F ratio as it applied to the variance between categories or groups over the variance within. So we'll draw similarities to this when we're calculating F ratio as it applies to the significance of the regression equation and the correlation coefficient. So our F ratio will actually determine the relationship between variables over the relationship that is independent for each x and y value. So again, as stated, correlation pertains to the relationship between variables whereby a change in one variable results in a concurrent change in the related variable. So correlation measures and describes the relationship between two variables. it focuses on two specific characteristics, the direction, which indicates either a negative or correlation, and denoted by a sign, positive or negative. And so if we're talking about two variables increasing, so as one increases, the other one increases, our x and our y, or we can say as x decreases, y decreases. So that's an illustration of a positive correlation because they're moving in the same direction. Or we can see that as x increases, y decreases. And again, that they're going opposite directions. Or we can say x decreases and y increases. So again, this denotes a negative correlation. So positive correlation means that they're moving in the same direction, negative in opposite directions. The form of the relationship we're going to focus on is a linear. There are other types of correlations, but for our purposes, we're going to focus on the form being related to a linear line relationship. And the strength or the consistency is denoted by the value, the numeric value. So their direction or type is the sign, and the strength or consistency of the relationship pertains to the value. And it says it varies from 0 to 1. In fact, it's -1 to +1. So here, 0 indicates no relationship. And a +1 would be a perfect. This +1 indicates perfect positive relationship. Similarly, for the negative, this would denote a perfect negative relationship. In other words, if x changes, we know exactly how much y will change when we're looking at r is equal to -1 or +1. In the social sciences, we won't see those values, but something close to +1 or -1. So the closer you get to +1 or -1, the stronger the relationship. And conversely, the closer you get to 0, the weaker the relationship. But again, all correlation coefficient values, R values, need to be put to a statistical test for significance. So in other words, you may see that R is equal to -0.98, which denotes a very strong negative correlation, but we cannot draw that conclusion until we test for significance to determine if that value was derived simply by chance or due to a true relationship between variables. So here's a relationship illustrated in what we refer to as a scatterplot graph, where we've taken our x values, our family income, and plotted them with the y variable, which is students' average grade, let's say on an exam. So we can see a pattern here as the family income increases, right, from 30,000 to 190,000. We see that the students' performance, academic performance, denoted by average grade, increases. So they're moving in the same direction. If we read it opposite, right, if we say as income decreases, right, then we see that students' average grade also decreases. So they're both moving in the same direction, so we see a positive correlation between these two. And that's also visually interpreted as the slope of the what we'll calculate later, the linear regression. So if you can envision a linear line centering or between all of these data point coordinates, we would see that it has a positive slope. But again, we need to refrain from concluding that family income causes students' average grade. We're just saying that they're related. And visually, we could guess that this R value, again, if we were just to guess, maybe somewhere close to about 8.85. Again, I'm just guesstimating based on the visual interpretation of these coordinates. It seems to be a very strong positive correlation. If you can take a linear object and place it, I'm just going to draw a line, linear line. And the closer those coordinates are to that particular line, the stronger the relationship between variables. So again, we're showing a very strong positive correlation. This value of 0.85 is just a guess of what that R value would actually equal if I were to calculate R given this data set. So again, we should remember to refrain from saying that family income causes students' average grade, but we see that they're highly correlated. But it doesn't mean that if your family received if your mom or dad received a salary bonus, let's say at the end of the year, they received a $30,000 bonus, doesn't mean that that's going to increase your GPA. Obviously, we would need to see that money spent towards tutoring or some other resources to increase a student's grade or performance, academic performance. So again, we see a strong relationship, but it is not a causal relationship between variables. So here's another illustration, a visual illustration. We're looking at the first example, temperature in relation to the amount of beer sold. So we see that as temperature increases, right, as temperature increases, we see a concurrent change in the amount of beer sold. So that also increases. So let's say we're at a ball game and we're looking at the relationship between these variables. Those who are stocking the beer for the day should recognize the warmer it gets, the more beer they're going to need on hand, because there's a strong positive correlation between these two variables. On the second example, and again, it's a positive, we see a positive slope, right, denoted here. Here we're seeing as temperature increases, that we see the amount of coffee decrease, right? As it gets warmer, consumers are going to purchase less coffee. We can understand that coffee is usually a beverage that we buy more readily when it's colder, but obviously we have iced coffees and all these other options where it's just simply a treat. But in terms of this relationship, as it gets warmer, we're going to sell less coffee. So again, it's a negative. So this is positive. They're moving in the same direction. And here we see a negative correlation, and that's also denoted by the slope of the line here. But both of them seeming to be very closely related to one another. So again, we would understand the positive as one increases, or X increases, or Y also increases. We can read it backwards. As temperature decreases, the amount of beer also decreases. And then for coffee and temperature, as temperature increases, right, the coffee sales decrease. So again, positive, negative correlation. Right, so here visually we're illustrating 4 different types of relationships. A shows a perfect negative correlation, so we would assume that R is equal to negative 0.10 because it has a negative slope, and it's a perfect correlation. They're all on the line. So as one changes, we know exactly how the other is going to change. So as X increases, we know exactly how Y is going to change. B shows that they're all scattered around, and there's really no way of, we don't see a positive slope or a negative slope. It's just really hard to see any relationship. So we would conclude that here R is equal to 0. There's no relationship between X and Y. We just don't know how they're related. In fact, we would conclude that they aren't related, that as one changes, there's no way of assessing how the other variable is going to react or be affected. In C, we see a positive slope. So as this increases, we see Y increase as well. And it seems to be fairly, strong. Again, if you take a linear object and put it over those coordinates, I'm just going to draw a line there to simulate that. And we might conclude that R here is equal to positive 0.8, or I would say maybe 0.9. Again, this is just an estimation. It's not an exact value. It's just giving you a sense of how you can perhaps estimate what the R is going to equal before you do your calculations. And then D, we see, somewhat of a relationship, and it appears to be producing kind of a negative slope between X and Y. As X increases, we're kind of seeing Y decrease. And so we would guess perhaps maybe negative 0.3 because it seems to be a very weak relationship. This was denoting very strong correlation between variables. No relationship. And perfect relationship between variables. So you'll have some homework questions like this perhaps where you're given a visual and you're asked to guess what the R may equal given our understanding of how they're related, what signifies a strong relationship versus a weak relationship, numerically speaking and visually. So again, the Pearson correlation R measures the degree, right? That's the numeric value, number value. The degree and the direction, is it positive or negative, of the linear relationship between two variables. A perfect linear relationship. Every change in x has a corresponding change in y. So again, perfect meaning r is equal to -1 or +1. So we know that if x changes, we know exactly how y is going to react. But that's very unlikely when we're working with humans, maybe more evident in the relationship between something in the hard sciences such as chemistry. But when we're working with people, it's very unlikely that we'd see perfect correlations between variables, although there is one example that's coming on a subsequent slide. So our R value, again, represents the covariability. The numerator represents the covariability, which we can interpret and understand as the variability that's determined by the relationship, or we can say how variables change together, covariability, over variability of x and y separately. So independent the denominator represents independent variability of x and y. So again, we want to assess the numerator, which represents how they change together, over how they change separately. And as you can imagine, we're hoping that the covariability outweighs the variability seen within each x and y variable. This is similar to our F ratio when we were looking at the variance attributed to between conditions over the variance of within. So again, determining, are we seeing changes because they're related, or are we seeing changes just because of random unsystematic factors? So the variability of x and y separately can be understood as, random chance variations. And the numerator covariability, that is x changes, we anticipate y would change as well if they're related. So now for the presentation of equations, sum of products, SP. It's similar to SS, the sum of square deviations, and in fact, SP is the sum of mean deviation products. So it measures the amount of covariability. Again, covariability understood as how they're changing together. And SP for the definitional of equation looks as we see here, SP is equal to the sum of our x mean deviation multiplied by the y mean deviation. So let's just take a look at SS for x. It would be written as the sum of x minus the mean of x squared. But that's also the same as saying, that's equal to saying the sum of x minus the mean of x multiplied by x minus the mean of x, right? We're squaring those mean deviations. So instead of doing that twice for the mean deviation of x, now we have the mean deviation of y. So the sum of products of mean deviation. So each x value deviates from the mean of x a certain amount, and every y value deviates from the mean of y a certain amount. And we're going to take those mean deviations and multiply them, and then do it for all the pairs that we have and take the sum of all those products of mean deviations. So again, by definition, it's very logical as to how we're computing these new statistics. The computational formula is different in the sense that conceptually we aren't seeing the emphasis on mean deviation because we're not computing mean deviation. So the definitional formula emphasizes SP as the sum of two different scores. The computational formula, on the other hand, results in an easier calculation. Again, it's more efficient, but doesn't lend itself as well to the regression equations we're going to learn. So our SP computational formula is as follows. We're going to take the sum of our x multiplied by its corresponding y, and then subtract what this quotient is equal to, the sum of x multiplied by the sum of y divided by n. And let's contrast that with our equation for the sum of products using the computational formula for one distribution. So it would be the sum of x squared minus the sum of x squared over n, which is the same as saying we're taking the sum of x multiplied by x, right, x squared, minus the sum of x, right, multiplied by the sum of x over n. So hopefully you can see the similarities that now we're adding this y value in place of this x value. So the structure is identical to the SS calculation, the computational calculation for each individual variable, and now we're combining those to represent the sum of squared deviation products. So we'll have the x multiplied by corresponding y. So I think that's helpful to see the similarities between these two equations. So again, our R statistic, the Pearson correlation coefficient, is a ratio comparing the covariability of x and y, the numerator, with the variability of x and y separately, expressed in the denominator. So again, we can think of the numerator, how variables are changing together, over how variables are changing independently. And again, based on chance, if we see a change in the x value from one observation to the next, is it due simply to chance, or is it due to the relationship with what the y variable? So again, how they're changing together over how the variables are changing independent of one another. And as you can imagine, we would hope that our R statistic is very large, meaning that the numerator is expressing greater change attributed to the relationship versus change attributed to chance that's expressed in the denominator. So I've gone over the basics of correlation, and we should understand that correlation is used, or the function or purpose of correlation is to help us with making predictions, and that relates to our linear regression equations that we'll learn how to calculate, validity and reliability. So first of all, prediction. If you have to submit an SAT, so SAT scores, SAT scores are used to predict college success. So the reason we universities ask for SAT scores is because we know that SAT scores are highly and strongly correlated with college level GPAs. So the higher the SAT score, the higher the GPA, and universities want to admit individuals that are going to be successful. So again, we use correlation to make predictions. The stronger the correlation, the more accurate the prediction. Makes sense. So the stronger these relationships are correlated, meaning as one changes, we expect the other one to change, either in the positive or negative direction. But if they're strongly correlated, then the prediction capabilities is increased significantly. Validity and reliability are kind of go together. That if we want to, let's say over the years we've seen changes in the SAT test or changes in statewide assessments of children K through 12, if we want to replace one test with another, we first have to validate that test. And to validate it means that we need to see a correlation between scores. So before that you can replace an SAT test, you first develop the test and then assess students and test them using the old test with the new test. And if the correlation between the two is high, we have now therefore validated the new test. If the correlation is weak, then we have not validated the test. That the test needs to test or assess what it says it's going to. And we can always use the original assessment as the basis of this comparison. So again, if the new SAT was not correlated with the old SAT's assessment, then we have not validated it. Reliability pertains to if we do these tests or assessments of validity over and over again, we'll get the same results. So the results are reliable. We can do this test of correlation over and over and over again, and if we produce the same or similar statistics, then we validated that test, but also it's reliable, it's consistent. So again, in order to replace a certain assessment, we've seen changes in IQ tests, so a new IQ test can't be used until it's been validated, and it's reliable when it's consistently producing the same results. Theory verification, we may want to assess the relationship between variables. The example that I walk you through for this chapter is the relationship between women's income and weight. So given our culture and society's pressures on women's physical attributes, we may theorize that there's a relationship between women's income and their weight, and we can collect data to affirm that that theory and test the correlation between these two variables. So again, we should understand that correlation can be used for any of these four reasons. And as we get into regression analysis, we'll focus on the function of predictability. How can we predict one value given the other? Interpreting correlations. Correlation describes a relationship. It does not demonstrate causation. So again, the limitations of the R value that's calculated may lead us to believe that there's a strong relationship, but we have to refrain from concluding that it's a causal relationship. Women's weight does not cause their income. Our height does not cause our height, or vice versa. Our height doesn't cause our weight, but those things are very strongly correlated with one another. So establishing causation requires an experiment in which a variable is manipulated. In other words, a true independent variable is necessary to speak in causal terms. So if we have an independent variable and we manipulate it, meaning that we randomly assign individuals to these different categories or levels of the independent variable, then we can talk about causation. But in correlational studies, technically we're talking about non-experimental studies, and we're collecting data, 2 data points from each individual, and neither of the variables are being manipulated. And this is demonstrated in the next slide, where we have 2 variables showing a very strong relationship, and our tendency is to say that one causes the other, but recognizing that we're just witnessing a very strong correlation between variables. So here is a very interesting example. We have number of churches and number of serious crimes. And so again, we take a linear object and draw a line, again denoting the relationship between the two. We see that it's a positive relationship, and we would assess that most likely R is equal to something very strong, positive 0.85. Again, I'm just guessing, but we see a very strong relationship. So one may, in error, believe that as number of churches increases, the number of serious crimes also increases, which, if you take a moment to think about that relationship, seems preposterous. that churches don't cause serious crimes, and we recognize that there are other variables at play here. One important variable to recognize that attributes to this correlation or this relationship between variables is the size of the population. And that's a greater factor or variable that helps explain this relationship, that we know that as population increases, the number of churches increases. Similarly, as the population increases, we tend to see higher rates of crime in a community. So again, we must refrain from explaining these relationships as causal relationships. They are simply relationships between variables, and we recognize that normally there are other variables at play that help explain this relationship. Correlations and restricted range of scores. So when we calculate R, which is the correlation coefficient, represents R, it is calculated using the data set provided. So we're limited in the range of scores that we initially collect in calculating R. Again, R is a function of those X and Y values in our sample data set. So we must recognize that severely restricted ranges may provide a very different correlation than a broader range. So as usual, we hope for large sample sizes. So large are best because they demonstrate a greater illustration of population values and give us a better sense of the existence of relationships in populations. So as usual, larger sample sizes are better. And we just recognize that we are restricted within the range of the scores that we initially collected. So to be safe, we never generalize a correlation beyond the sample range of data. In other words, if we want to make predictions of someone's college GPA based on their SAT, those predictions will be limited to the data collected, so the range of SATs and the range of GPAs initially collected, and we could not go outside of that range to make predictions of individuals' GPAs based on their SATs if it's not within the original data set collected. So here's an example of drawing conclusions using a restricted range of data. So in the circle over here, this represents the data that was collected. Visually, we would conclude that it appears that R is equal to 0, that there doesn't seem to be a relationship between the variables. But if we collect a larger data set, right, and calculate our R, now we're talking about all of this data. And here we see that we see a very strong positive correlation between variables, and we have a better understanding of the relationship between variables opposed to that restricted range that we initially collected information on. So this essentially tells us larger sample sizes are better, that they're going to be more reflective of the population relationships between variables versus a small data set. It's hard to draw conclusions based on small data sets. Correlations and outliers. An outlier is an extremely deviant individual in the sample, so something very different from the other data points that are collected. They're characterized by much larger or smaller, could be a very extreme small value or extreme large value, that has an effect on the interpretation of the variables that we're comparing or testing in terms of relationship. In a scatter plot, the point is clearly different. So that's why it's important to construct scatter plots either by hand or using Excel to see the visual interpretation of the data. Sometimes in a table it's not as evident, but when we put it in a scatter plot, those outliers are more apparent. So the outliers produce a disproportionately large impact on the correlation coefficient, as we'll see in the next slide. So here our table, it's a very small data set, but we see X and Y, and we plot in the scatter plot how they're related. Visually, we see that there's a very small, no relationship between the variables. They're kind of scattered randomly around. As X changes, we're not really sure how Y is going to change because they're not related. and the R value has been calculated. It's actually equal to negative 0.08. So showing that these two variables are not related to one another. Now here we add F, right? One more observation is drawn, and the X is 14 and the Y is 12, and we plot that, and now see the visual. It changes what we originally thought the relationship was, and numerically speaking, now we produce R is equal to positive 0.85, which is significantly different than what this interpretation was of the relationship between the data. So the majority of the scores are showing that they're not related, but adding that one outlier produces something that makes us believe that there's a strong relationship and positive correlation. So without the scatterplot, we would just have calculated 0.85, and that would lead us to believe that this is a significant positive correlation between variables. But the visual that we see in the scatterplot helps us see that in reality, these values are not related to one another, and it's just this one outlier that makes it appear as if there is a relationship between these variables. So again, affirming the importance of the scatterplot to visually interpret our R value. If we were to put this R value to a statistical significance test, most likely it would not pass the test because, again, we're not seeing a relationship between these values. Okay, so a little more basic information about the correlations and the strength of the relationship. So a correlation coefficient, again, that refers to Pearson's R, measures the degree, right? That's the number value. The degree is measured by the numeric value of the relationship on a scale of 0 to 1. In fact, it's -1 to +1, and we discussed how 0 illustrates no relationship, +1 perfect positive correlation, -1 perfect negative correlation. Because these values are represented as proportions, it's a decimal. It appears to be a proportion, but just because it's a decimal doesn't mean that we would express it as a percentage or proportion. And the reason we don't do that, because again, it's just a ratio of these variations, and it ranges between -1 and +1. So refrain from expressing it as a percentage or proportion. It's just the value within this set range of -1 to +1. The squared correlation may be interpreted as a proportion of shared variability. So R squared is referred to as the coefficient of determination. Similar to what we've used R squared to do in a t-test, it's the percentage of variance attributed to treatment. R squared, or coefficient of determination, is expressed as the percentage of variance in one variable that can be explained by the relationship with the other variable. So if we see a change in our Y variable from one observation to the other, so again, if we're talking about individuals, it's not within that individual's data. It's from one observation, one individual to the next individual. So if we see an increase in SAT scores, then a certain percentage of that change from one SAT score to the next observation of SAT score in relation to the GPA is attributed to the relationship. So the percentage of variance in one variable, let's say GPA, that can be explained by the relationship with the other variable, its relationship with the SAT scores. So it's similar to how we've interpreted in the past, but now it's referred to as the coefficient of determination. We're trying to determine the variability that we're seeing in one variable and attributing that variation to its relationship with the other variable. So again, here we're just reiterating what I just stated, the coefficient of determination measures the proportion of variability in one variable that can be determined from the relationship with the other variable, the shared variability, in other words. So let's say r is equal to 0.8. So r squared would equal 0.64, and we would say that 64% of the variability, let's say in y, can be determined by its relationship with x. So let's say x is SAT scores, y is GPA, right? The change in GPA is attributed to its relationship or correlation with SAT scores. So again, we express it as percentage of variation that is explained by their relationship, the shared variability. And as you can imagine, the larger or the stronger the relationship, I should say, the higher the coefficient determination. So that should make sense that if they're really strongly related, the ability to determine the variation or explain the variation in one as a result of its relationship with the other becomes higher. The percentage increases as our R value increases. So here are some more examples. We have A representing the relationship between shoe size and IQ. And the visual tells us that most likely R is equal to 0. We see no relationship between variables. And it's important to say that when we get to regression equation calculations, the purpose of those are to make predictions. So if we look at the center, this would represent the average. Let's say we're talking about women. Their average shoe size is 8 and average IQ is 100. That if I were to keep rattling off shoe sizes, right, size 9, what do we predict that their IQ would be? Well, we can't really say for sure, so our best prediction would be the mean, right? The mean of the other variable, IQ, is 100. Let's say the woman has a size shoe of 10. What would we guess for IQ? We would guess the mean of that distribution because that would be the best default prediction because the relationship is 0. There's no relationship. That is, as x changes, we don't know what's going to happen to y because they're not related. If she has a shoe size of 7, again, we would predict that her IQ is equal to 100. No relationship. And vice versa, if we were to rattle off different IQs, our best estimate of that woman's shoe size would be the mean, which would be 8. The next one is showing us a relationship between IQ scores and GPA, and we see that it has a positive slope and it appears to be pretty strong. Maybe R is equal to, R is equal to, let's say, 0.75. So strong positive correlation between two variables. And the last one shows positive 0.10, a perfect correlation. So let's say your annual salary, obviously, and I said it would be rare to see these kinds of relationships, but here's a perfect numeric value that shows a positive perfect correlation. So let's say you earn $2,000 a month. So we want to determine what your annual salary would be with each passing month. So January, your monthly salary is $2,000. So your yearly salary would be $2,000. And then we go to February, and we would recognize that you now would have a monthly salary of $2,000. So the annual salary, we go up 1 month, and now you have $4,000 as the annual based on the increase of months. Actually, it probably make more sense, and again, this isn't perfect, but if we talked about the month, just denoted this as month 1, that would make more sense. 2, 3, so we have 2,000 here, right? 1 month later, you have 4,000. 1 month later, 6,000, and so on and so forth. So we know exactly how much your annual salary will be with each passing month, because there's a perfect correlation that if each month you earn $2,000, after 3 months you'll have earned an annual salary of $6,000. So again, just giving you a quick illustration of a perfect correlation between two values. Again, if your salary is absent of any bonuses, this would be the case. And annual salary is divided into 12 equal portions of income. And as it indicated earlier, that once we calculate our Pearson correlation coefficient, we can't automatically make conclusions about the relationship between variables. We have to put that statistic to a test. So we can conduct a test of significance using our correlation coefficient. And so our population correlation, again, as I indicated earlier, is referred to as rho. Looks like a P, but it's not actually a P. It's referred to as rho. A non-directional hypothesis is going to say that rho is equal to 0, and the research would say it's not equal to 0. A directional hypothesis would look like this, where rho is equal to or less than 0, and the alternative would read that rho is greater than 0. So greater than 0 implies positive correlation. Directional again. And then rho is greater or less than 0, and that alternative hypothesis indicates that rho is less than 0, so we interpret that as a negative correlation. And the non-directional means that we can produce, end up with a positive or negative correlation, just not equal to 0. So to conduct our test of significance, we'll compute a new t-statistic similar to the same structure as our t-test that we saw in the previous chapters. So the sample correlation R used to test the population, rho. Degrees of freedom in this case is n-2. The hypothesis test can be computed using either T or F. We'll demonstrate T as it relates to correlation. We'll conduct an F test when we look at regression equations. And we'll use our t-table to find the critical value using degrees of freedom equation of n-2. So again, R represents our correlation coefficient minus rho, which is the hypothesized population correlation, over a standard error estimate. So our new standard error is this calculation here, which is simply taking 1 minus our correlation coefficient over degrees of freedom and taking the square root of that value. And that t-statistic, again, will be compared to a critical value to draw conclusions regarding the null hypothesis. When we conduct our test of significance, as we've learned thus far, our conclusions include certain notation, and we're told here that it would include our R value, the sample size, our probability statement, and then whether or not we conducted a one or two-tailed test. And as indicated, one of the functions of correlation is to make predictions. So we're going to learn about linear regression equations to be able to make predictions given one value. The Pearson correlation measures a linear relationship between two variables. We've established that. And it helps us, it illustrates the obvious relationship between these variables. The line through the data makes the relationship easier to see. Shows the central tendency, again, chapter 3 was central tendency, the mean, median, mode. So we can understand that the line is kind of the default relationship that we see between these two variables, the predicted values, and can be used for prediction. So regression analysis precisely defines the line. So we're going to learn how to compute these equations so that we can make predictions. So again, the line represents what we refer to as the central tendency, how these variables tend to relate to one another. And the blue data points are the actual values or coordinates. And the line is constructed using the predicted values of y given x. So if we know what x is equal to, let's say SAT values, and we want to predict GPA, we can construct these regression equations to make those predictions. And the difference between the actual and predicted we refer to as the error. But again, understand the line as representing the central tendency or the default relationship between these two variables. Continuation of linear regression will be presented in a subsequent video. So that's the end of this particular video. We'll pick up where we left off in part 2.